Now I will begin with 2015 C3 surface geometry. So on my A3 page here I have already set up the plan and elevation of the given structure. All very straightforward. The only thing to watch out for obviously is your scale, so everything is divided by 200, as you'll see your scale there. Part B of the question, determine the dihedral angle between surfaces A and B. Now as you can see, we can see surface A in the elevation and plan, surface B in the plan here. It's actually hidden in behind surface A and C here in the elevation. We can't see it fully. So what I will do is I'm going to identify my line of intersection, okay, which goes from the apex of the structure to point P here. So I will call the apex point O. So OP is the line of intersection. Surface A is OPQ. I will call surface B then OPR. And I'll follow my point up. So for my dihedral angle then, the first thing I need to do is get the through length of my line of intersection. As I said, my line of intersection is OP. So to get the through length of that, I will project 90 degrees to it. And I'll put in my x1, y1, and heights from the elevation. Now as you can see, Q and R are both on the xy line. So there's Q1, R1. Take my height for P. And O. There is O1, P1, and that is the true length of my line of intersection. And then I'm just going to draw in my surfaces A and B, like so. Next step for finding the dihedral angle, we look along our true length line, so we're projecting off that way. Now I am going to put in a datum line between my x1, y1 and my plan. So there's my datum line, which I will label. O and P are the same distance from the datum line. R is on the datum line. And here's point Q. And there's my dihedral angle, which you will measure and write in also. So that is part B of the question. And next step then, part C, we're asked to draw the true shape of surface C and hence determine the radius of the largest circle that can be contained within the surface. I'm going to break that into two parts. So first part, draw the true shape of surface C. So there's surface C. It is a triangular surface, as you can see. It is also a vertical surface in the plan that appears as just a line. So what we will do is rabat surface C in the plan here. So we're going to rabat it on this baseline of it, which in my drawing is QR. The reason we're rabatting it on that line is because QR is horizontal in the elevation, therefore it is a true length in plan. So I need to find where point P is now in my plan view. So as I'm rabatting it on the line QR, I will project out my point P 90 degrees to it there. Next step, I know the height of my vertical face here, so I'm just going to measure that height there, step it off, turn in the plan, that is point P rabatted, and there is my true shape of surface C. The second part of the question, determine the radius of the largest circle that can be contained within the surface. That is an inscribed sphere. So to get an inscribed sphere, we bisect any two of the angles of that triangular face. Now I actually already have this angle here bisected. That projection line bisects it, so I'm going to bisect one or the other. Doesn't matter which. And there is the largest circle that can be contained on that surface C, which is part C of the question done. Next part, D1, determine the pitch of surface A. What they mean by pitch is the angle between surface A and the horizontal plane. Another that would also come up sometimes in intersecting planes, where you will be asked to find the true inclination of surface A to the horizontal plane. So what we need to do is get an edge view of surface A. So to get an edge view of surface A, the first thing that we do is we put a horizontal section. So we're going to put a horizontal line which cuts surface A in the elevation. I will put that in from point P straight across there. I'm going to call that there point S. I'm going to drop down point S. Now the line from P to S is a true length line. I know it is a true length line because it is horizontal in the elevation. And all I need to do then is look along that true length line. There's my x1, y1, heights from the elevation. So point Q is on the xy line. There's Q1, P and S both the same height. And as you can see, all 3 points line up, and that angle gives me the pitch. The last part of the question: a lightning conductor is to be fitted to the building. The conductor cable is to run from the apex of the building along the outer edges of surface A through point P and down to the ground at Q. Determine and indicate in meters the minimum length of cable required. So the cable is going to run from the apex, which I had called point O, to point P, then to the ground at Q. So I need to find the true length of OP and add it to the true length of PQ. I have already found the true length of OP over here. So to find the length of this cable, all I'm going to do is put in a light horizontal line down the bottom of the page here. The cable starts at point O. I'm going to pick a point there, call it O. Measure the true length of OP from here. Step it off. OP, there's the first part of the cable. Then I need to find how far it is from P to Q. If you remember, we have found the true shape of surface C here. PQ, there's the true length of PQ. So I will measure that length, step it off from point P, and that then is the length of my cable. Now it asks you to determine and indicate in meters, so measure the length of that cable, scale it back up, multiply it by 200, write your answer in meters, and that will finish the question for you.